This is our introductory video to stoichiometry. So what is stoichiometry? It's a very common topic that I believe you've been dealing with from high school, and so I'll try to make it as interesting as possible, and I believe you enjoy the journey of chemistry. Okay, so we can define stoichiometry to be the study of quantitative relationships in substances and their reactions. So the key term is quantitative. So quantitative means quantity, right? So what it means is we can use this illustration. Assume we have two reactants A and B reacting to give us C and D. Okay, so what we're trying to study under stoichiometry is basically the relationships that are there between these reactants and also their products. So in that regard, if you are given the masses of, let's say, both A and B, you should be able to find the masses of what? Of your products. You should be able to find. So apart from having our reactants and their products, we also have, they do come with stoichiometric coefficients. Let's say we have a 2 there, we have a 4 there, and then let's say you have just the 1 there, and then let's say a 3 there. So we call these are called Moore ratios, and you realize that they're going to be very useful in terms of forming relationships among our reactants and also between the reactants and the products. So under the study of this topic, it's very, very important that we understand how we get to balance chemical equations, how we get to calculate the mole and the molar masses, how we get to determine the chemical formulas, how we get to determine the mass relationships in equations, how we get to deal with the limiting reactant or the limiting reagents. All these are going to be very useful for the study of our stoichiometry. Of course, as we get to proceed, we'll talk about other things that are concerned with stoichiometry. So for a practice question, how many grams of water will be formed when 48 grams of hydrogen gas are mixed with excess oxygen gas? So looking at this question, being taught to say water will be formed tells us to say it's going to be a product. So products are the ones that appear on the right hand side of the equation. And then when 48 grams of hydrogen and excess oxygen gas are mixed, so that tells us to say hydrogen and oxygen in this case are our reactants. So reactants appear on the left hand side. So we do understand, and from the given example, even just the way hydrogen is written, hydrogen is diatomic. So even anything that is diatomic has got a subscript of a 2. So we have hydrogen reacting with oxygen. We also know oxygen exists diatomically. Okay. So what products do we have? So in this case, we've been told to say water is what is being produced. So now, how do you get to balance this equation? Before we could get to perform any calculations, we need to balance this equation. So look at the right hand side and the left hand side. We'll start first of all by comparing the hydrogen. We have two hydrogen atoms. We have two hydrogen atoms. So that's fine for now. Go to oxygen. For oxygen, we have 2. On the left, we have 1. How do we balance it? So we can put 1 over 2 there. So 1 over 2 and the 2 will give us a 1. So it's a balanced equation. But this is not the way we get to balance our equations. We don't want to put fractions. Okay. Except this will be done later on when we're asked to write what we call enthalpy formation reactions. That's when you use the fractions. But under this case, we want to make sure that everything has got no fraction. So this fraction that we've introduced has got a 2. So multiply the entire equation by a 2. So we have 2 hydrogen plus O2 giving us 2 H2O. At this point, if you begin to compare, we have got 4 hydrogen atoms. We have 4 hydrogen atoms. we have two hydrogen oxygen atoms, and then we also have two. So this 2 multiplies everything that is after it, both the H2 and the oxygen. Okay, so the 2 gets to multiply against the subscript to give us 4, and against oxygen to give us 2 oxygen atoms. Of course, we understand all these are in gaseous state. Of course, our water is in liquid state. Okay, so in this case, they were not asking us to write the equation. We are just trying to balance it for the sake of us getting to answer the question. Okay, so it's also okay with you being able to answer the question directly without the need of introducing a fraction like others do. So all you'd have to do is just try to observe, but in that case it takes a bit of some time for you to be able to see what you can do. So we have 2 oxygen atoms, you have a single one there, so we can put a 2 there to balance, and then that will make us put a 2 there so that we balance the hydrogens as well. So you are at liberty to choose which one is easier for you. Okay, so how many grams of water will be formed when 48 grams of hydrogen are mixed with excess oxygen gas? So the key term is excess. Excess means it's more than enough. So therefore, in this case, the limiting reagent is hydrogen. We'll understand later what a limiting reagent is. So we always use the limiting reagent to determine how much of the product was formed and how much of the other reactant reacted. So in this case, we're interested in the 48 grams of our hydrogen. So we'll use that to determine the grams of water that were produced. Okay, so how do you handle that question? So basically, the basic idea is we need to determine the number of moles. So number of moles, I want you to understand that is given as the mass divided by the molar mass of that substance. So what is the mass of our hydrogen? It's 48 grams. So the molar mass is what you get on the periodic table. So make sure that whenever you're having something diatomic, you need to consider that. So we have a subscript of a 2. So that 2 is going to multiply against the molar mass of hydrogen. So if you go on your periodic table, the molar mass is the bigger number. So if you look at hydrogen, it has got a subscript of a 1, which is we call the atomic number. So on top is 1.008. So that is our mass number. For oxygen, there is 16 and then 8. So the top part is the molar mass. So gets to perform the calculation there. So 2 times. So now notice that I'm only using the subscript. I'm not using the coefficients. I'm using the subscript. So if we had a 3 there, I was going to multiply by a 3. Okay. So now grab your calculator there and perform the calculation. You'll see what you're going to have. So we have 48 divided by 2 multiplied by 1.008. So what answer are you getting? So 2 by 1.008. Divide that into, so we have 48 divided by boss calculator very good. 48 divided by 2, 1.008. So the answer I'm getting is basically 23.8095 moles. So we have the number of moles. So this is a point where now where we get to introduce the use of the mole ratios. Okay. So the number of moles that we found are for hydrogen. So I'll put H2 there. Now, we want to find the grams of water that will be formed. Now, notice one thing. These guys are in the ratio of what? They're in the ratio of 2 to 2. So, a ratio of 2 to 2 tells us to say they're in the ratio of 1 to 1. So, in that regard, what that tells you is the number of moles that we've calculated for hydrogen are the same for water as well. If we had a different number, let's say for water, if we had, let's say a 4, the ratio was going to be 2 to 4. In that case, we would have written the number of moles that we found, 23.8, and then we try to find the value of x. But in this case, they are in the same ratio, so they have equivalent number of moles. So we have the number of moles. I believe we are able to find the molar mass of water, right? So what is the molar mass of water? So the molar mass of water will involve the addition of, we have 2 hydrogen atoms, so 2 multiplied by the molar mass of hydrogen plus oxygen, which is 15.998 if you check your periodic table. So let's basically get to add the 2 by 1.008 plus 15.998. So the molar mass, the relative molecular mass of our water molecule is 18.014. Now the units are grams per mole. Okay, so we want us to find the mass. So we have 18.014 grams per mole. Now we have the number of moles which are coming from hydrogen. Since they are of the same ratios, they have got the same number of moles. So you multiply like that. So notice that the number of moles are going to cancel out. So 18.014 multiplied by 23.8095. Our answer becomes 428.9 grams. So we need to go back to our question and observe something, the number of significant figures. So 48.0. So in that case, we have 3 significant figures. So I want to make sure our answer is also 3 significant figures. So therefore our answer becomes 42. And then because the number is greater than 5, we'll add the 1 to 8. It becomes 429 grams as our solution. Okay, so take note of that. So in summary, the formulas that we've come up with is the number of moles is mass over molar mass. So the molar mass can also be the relative molecular mass in case of a compound, or relative formula mass. So we had calculated the relative molecular mass of water, and then we have the number of moles determined using the equation. So we're able to find the mass. So you can make mass a subject by multiplying the number of moles times the relative molecular mass or formula mass, as we've observed. Or you can use what we are calling dimension analysis, which is basically what we've introduced. And with this solid foundation, let's proceed to more advanced concepts on stoichiometry. So we'll introduce how to balance basic simple chemical equations. So write a balance equation for the reaction of molecular nitrogen and oxygen to form dinitrogen pentoxide. So I believe that at this stage we already understand that nitrogen exists atomically as given, as well as oxygen. Okay, so di means 2, pento means 5. That comes from the names of the polygons. Okay, so pentan, so that is where the pento is coming from, the pent, sorry, and then oxide is oxygen. So write a balanced chemical reaction for molecular nitrogen and oxygen to form. So what forms is a product. So dinitrogen pentoxide. Di means 2. So N2, pent means 5. So oxygen subscript 5. So that's what dinitrogen pentoxide is. Okay. Now we need to balance this equation. So we'll try to observe a number of atoms on the left and the right hand side. So I'll start first of all from nitrogen. Look at nitrogen. On the left we have 2. How many do we have on the right hand side? There are 2. So that is okay. Let's observe oxygen. Oxygen has got 2. On the right hand side there are 5. So is it balanced? It is not balanced. So where do we have a greater number of hydrogen atoms? We have a greater number of hydrogen atoms on the right hand side. We have 5. On the left hand side we have 2. So how do we get to balance that? Okay. So the basic idea is we have 2 and 5. So how do we balance that? So I can decide to get a bigger number, which is 5, and I'll multiply against 2. But that would give me 10. So I'd have to put a 2 on the bottom. So that is 5 over 2. So 5 over 2 times 2. 2's will cancel out, remaining 5. So we can use 5 over 2 to balance. So I can say 5 over 2. So 5 over 2 tells us to say the 2's will cancel out. Not necessarily that we are supposed to cancel them from the equation, no. Just have that in mind. So at this point, we have 2 nitrogen atoms, we have got 5 oxygen atoms, and then we have 5 oxygen atoms. So they are all balanced. But when we are balancing equations, they want us to balance with all numbers. So we'd have to multiply the entire equation by the fraction. What number do we have on the bottom? We have a 2. So multiply the entire equation by a 2. So there is a 1 there. So it becomes 2 nitrogen plus, so the 2 will cancel out that 2. Yeah, we remain with 5 oxygen atoms. And then here there is a 1. So it will just become 2 nitrogen dinitrogen pentoxide. So you can try to count again. We have 2 times 2, we have 4. On the left as well. On the right, 2 times 2, we have 4 as well. 5 times 2, we have 10. 2 times 5, we also have 10. So you can now observe that the number of nitrogen and the oxygen atoms are balanced in this equation. So feel free to attempt the 2 questions. You're at liberty of pausing the video and try them out to see if you've understood. So reaction of ethane, which has been given with oxygen to yield water and carbon dioxide. So quickly write the equation. Oxygen exists diatomically, so O2, to produce water and carbon dioxide. Let's observe. How many carbon atoms do we have? We have 2. On the left we have 1. So already that is the starting point. I can put a 2 there. So we've balanced the number of carbon atoms. How many hydrogen atoms do we have? We have 6. We have 2. So I can put a 3 there. So now notice that I didn't start with oxygen. So don't start with a reactant that is contained in more than one compound, because oxygen is part of water and also carbon dioxide. Starting with it would be a very bad idea because it can become very difficult for us to balance. So start with the ones that are at least existing in only one compound. For example, hydrogen only in water and carbon only in carbon dioxide. Okay. Now we can go to our oxygen atom. So we've balanced hydrogen and we've also balanced carbon. So observe that 3 times the oxygen atom, we have 3 there, and then 2 times 2 there, we have 4. So 3 plus 4 gives us 7 oxygen atoms on the right hand side. And on the left hand side, how many do we have? We have 2. So 7 is an odd number. We cannot balance it. So we can only use a fraction again. We'll just say 7 over a 2. The 2 is going to cancel with a 2. So we have 7 on the left as well. But notice that we can't leave our answer in fraction form. So that requires us to multiply now the entire equation again by what? By a 2. So just do that. So there's a 1 there. So it will become 2. The 7 over 2 itself, the 2 cancel out. Will just remain with a 7. The 3 will become a 6. The 2 will become a 4. So that is our result after multiplying by a 2. You can try to observe. How many carbon atoms? 2 times 2 is 4. We have 4. Hydrogens, 2 times 6, 12. 6 times 2, 12. Oxygen, 7 times 2, 14. 6 times 1 oxygen gives us 6. And then 4 times 2 gives us 8. So 8 plus 6, 14. So we've balanced the equation. For the second one, molecular nitrogen and molecular hydrogen to produce ammonia. So do you know what ammonia is? So ammonia is NH3. Okay. So in case you didn't try it out, you can try it out. So nitrogen exists diatomically. Hydrogen also exists diatomically to give us ammonia. Observe first. Nitrogen we have 2, on the left we have 1. What can we do? We can put a 2 there. Hydrogen, how many do we have? We have 2. On the left, at this point, how many we have? 2 times 3 is a 6, right? Is that okay? So, not a 6 necessarily, a 3. So that it will give us a 6 as well. So we've balanced. The number of nitrogens are 2 on the left and the right hand side. The number of hydrogen atoms are 6 on both sides. What if you decide to start with balancing hydrogen? What happens? So we have 3 hydrogen atoms and 2 hydrogen atoms on the left hand side. What if you try? So the only way you can balance is we have got 3 there as a subscript, so we can multiply the entire one by 3. Now that will give us 6, so I would have to put a 2. 3 over 2, which is going to give us a 3. And then nitrogen, we have a 2 there. So on the right hand side I have 1. So I can put 1 over 2. Because I don't want to put a 2 there, because if I put a 2, it will affect the hydrogens that have already balanced. So at this point you can multiply the entire equation by 2. So the 2 cancel out from the first part. So which gives us the same answer. So irrespective of what you start with, you're going to get the same answer. Let's now try to understand basically what the relative atomic mass, relative molecular mass, and relative formula mass are. So to start with, relative atomic mass, which is denoted as RAM, which is relative atomic mass. So how do we define the relative atomic mass? So the relative atomic mass of an element is defined to be the weighted average of the masses of the isotopes. So the weighted average of the masses of the isotopes in the naturally occurring element relative to the mass of an atom of the carbon-12 isotope, which is taken to be a 12. So when you get to find an average of the masses of the isotopes of the element that are occurring naturally, and then relative to the mass of an atom of a carbon-12 isotope, basically what you get is a relative atomic mass. So relative implies you're comparing against. Okay, so you compare the weighted average masses of the isotopes in the naturally occurring elements. So it should be naturally occurring elements relative to a mass, relative to the mass of atom of carbon 12 isotope. So that is what we call relative atomic mass. So without complicating things further, I would want to make a comment to say, when you look at the periodic table, when you look at your oxygen, for example, you can use it as an example, or we can use both oxygen and carbon. So let's say on top you'll be able to see 15.994. Of course, on some periodic table you get to see 16.4, but it's exactly 15 point something. And then on the bottom you have 8. So that value that you're seeing on top is what we call the relative atomic mass in simplicity. So if you look at carbon, it is 12.01, and then we have a 6. So basically that is the relative atomic mass of what? Of our carbon. So one thing that I would want you to understand again is the fact that when you talk about a mass of an atom, the mass of a single atom is just too small. Okay, an atom is the smallest particle of an element that can take part in a chemical reaction. So it is just too small. It is impossible for us to put it on a scale and weigh it. Okay, so therefore atomic masses are defined in terms of what we call the atomic mass unit. So we have what we call the atomic mass unit. Those are the units that we're going to be using whenever we're talking about atoms. So we use what we call the atomic mass unit, usually denoted using a small letter u. So when you say 2u, it means 2 atomic mass unit. Okay, so 1 atomic mass unit, for your information, is basically equivalent to 1 point, let me write that better, 1.66 times 10 to the power negative 27 kilograms. So what is an atomic mass unit? So it is very difficult for some people to remember this value, but what I usually emphasize is you can think of it in this way. I believe you've been working with Avogadro's constant, which is 6.022 times 10 to the power 23 for quite some time now. So 1 over the Avogadro's constant in grams is equal to 1 atomic mass unit. So if you get to perform the calculation there, you are dividing the 6.022 times 10 raised to the power 23, divide that into a 1. So the answer that I'm getting is 1.66 times 10 to the power negative 24 grams. So now you know that for you to move from grams to kilograms, you need to divide by 1,000. So dividing by 1,000 will imply you get to subtract 3. So if you subtract a 3 from the power, it will become negative 27, which we have in our kilograms there. So I don't know which one is easier for you to remember. Either you work with 1 over Avogadro's constant to be equal to a gram of one atomic mass unit, or you just master this constant. But usually in your assessments it will be given, so no need of you worrying much about it. Now what about if you talk about what we are calling the relative molecular mass? What gets to come to your mind? What is the relative atomic mass, or relative molecular mass, which is the mid one? Since we've already talked about the relative atomic mass, which is shown on our periodic table, how do we get to define the relative molecular mass? So we can basically talk about the relative molecular mass to be the summation. It is the sum of the relative atomic masses. So what we are from talking about. So the summation of the relative atomic masses of the atoms in a given molecule. So what is what the relative molecular mass is? So what that means, if you are given carbon dioxide molecule and then they ask you to find the relative molecular mass, it implies you need to add to sum up the relative atomic masses of the atoms. Okay, so the simpler calculation is we have 2 atoms of oxygen, we have 1 atom of carbon. So oxygen, if you go to your periodic table, we are saying summation of relative atomic masses. Go to your periodic table, you'll find something like 15.994. Look at carbon, 12.01. So the key aspect is being able to identify how many atoms are present in a molecule and then multiplying against their relative atomic mass, and then you get to sum up the results. So multiply what is on top, 2 times 15.994, and then plus, I'll do that again, 2 times 15.994 plus 12.01. So the answer is 2 times 15.994 plus 12.01. So the answer is 43.998. So units used, grams per mole. So basically that is our relative molecular mass. So when you're talking about the relative formula mass, on the other hand, we can use the same definition. We can just say the relative formula mass is basically the summation of the relative atomic masses of the atoms in a given formula of a substance or compound. So all the same. So if I give you a formula, let's say calcium hydroxide, so what you're going to find as a summation of the relative atomic masses of all these atoms is what we are calling the relative formula mass. So it will involve you recognizing and understanding the use of the subscripts. So in this case, these two will multiply to everything inside. So that means that we have calcium plus 2 oxygen plus 2 hydrogens. So substitute their values from the periodic table. So check for the relative atomic mass of calcium, substitute for oxygen and hydrogen as well. So that summation that you're having is what we are calling now the relative formula mass. Now just one more example that I can mention of that you need to understand is let's say we have magnesium and then nitrate. So this one looks a bit tricky and students usually get to make mistakes. So here it will be magnesium. Now we have a 1 there for nitrogen, so it will be 2 nitrogens. And then 2 times the 3 for the oxygen, it will be 6. So we have 6 oxygen atoms. So substitute there and then add the answers. What you are going to get is the relative formula mass of magnesium nitrate. So I believe you now understand what the relative atomic mass is, the relative molecular mass, the relative formula mass, and how to convert from atomic mass unit to a gram or kilograms. So in the next tutorial, we're going to understand how we get to determine the relative atomic mass calculations from the isotopes. Okay, let's say you're given carbon 12, carbon 13, and carbon 14, and then they ask you to find the relative atomic mass, because what we see on the periodic table is the relative atomic mass, but there are atoms that exist in more than one form in the natural form. So we'll try to understand how we get to perform those calculations. Okay, let's try to talk about the relative abundance of isotopes. So we basically know that isotopes are atoms of the same element with different mass numbers. So examples is we have carbon 12, carbon 13, and carbon 14. So when you look at these guys, they have got the actual masses, atomic masses to be as indicated. So for carbon 13 is exactly 13.003355, but it is called carbon 13. Of course, if you talk about carbon 12, it's exactly 12. And then These have got percentages of existence, or which we are calling the relative abundance by percentage. So this one is 98.89%. Carbon 13 is 1.11%. Carbon 14 is 1 by 10 to the power negative 10 percentage by percent, which is a very small value, 0.00000. Imagine having 10 zeros, which is just too small. So its value is negligible. So when you look at the periodic table, we can't show all the isotopes because we're just going to have too many, because many atoms have got many elements have got isotopes. So we use what we call the relative atomic mass, which is derived from the isotopes given the abundance and the atomic masses. So we're going to demonstrate how come on our periodic table for carbon we have 12.01. So it's not like the 12 was gotten from the 12. Like I've said, this 12, as you've seen, is exact. So how come we have 12.01? Where does it come from? Okay. So the fact that this one is higher in terms of abundance, it has got the higher effect on the average. So therefore, let's try to calculate. Relative atomic mass is basically the atomic mass multiplied by the abundance plus. So we'll do the same for the others as well. So this formula depends on how many you are given. In this case, we are considering only 2 because the 14 is negligible. We are able to ignore it. Okay. So let's try to perform the calculation there. So for carbon 12, the percentage is 98.89 over 100 plus 13.003355 multiplied by 1.11. Okay, so grab your calculator there. 12 multiplied by 98.89 divided by 100 plus 13.003355 multiplied by 1.11 divided by 100. So the answer that I'm getting is 12.011, and other values there. 1 again, 3, 7, 2, 4. So rounding off answer to 4 significant figures, our answer becomes 12.01, which is the value that you see on the periodic table. So it is derived from the isotopes of carbon. So this applies to all the other isotopes, elements with isotopes: copper, bromide, talk about chlorine as well. Given its isotopes, you should be able to find the relative atomic mass if you are given the abundance. Okay. So what if they give us the relative atomic mass and then they ask us to find the relative abundance? How do you go about that? So that's the second question that we have. So if the masses of one isotope of nitrogen is given, so we have the atomic mass of nitrogen 14, and then we also have for nitrogen 15. Find the relative abundance of the isotopes given that the relative atomic mass is that. So we've been given the relative atomic mass. Remember, our formula is the relative atomic mass is equal to the atomic mass multiplied by the abundance, just like that. So substitute quickly. So we have 14.007. So in this case, what we are finding is different. Okay. So I'll use X to denote the abundance. So if we have X, we expect that the other one is going to be 100 minus X. What it means is, if you have 40, for example, it means the other one is going to be 100 minus 40, since there are only 2, which is obviously 60, right? Okay. Now, to make our calculations easier, we'll rather take everything in terms of divided by 100 by 100. So that you have 0.4 and 0.6. So therefore, instead of saying 100 minus x, we'll say one will be considered to be x by percentage, the other one will be considered to be 1 minus x. We've divided everything by 100. Okay, each time we work with this, it's easier. So I'll start with nitrogen 14. Nitrogen 14, the actual atomic mass is 14.003. So consider that one to be x by percentage. Plus, the other one is going to be 15.000 as seen, and then it will be 1 minus x. Okay, so you use these. This is what is very important in terms of our calculations. So quickly we try to find the value of x. So multiply by 15. You have 15.00 for the one, and then again you have minus 15.00x. So connecting the like terms, on the left hand side we have 14.007. This one will go the other side to be 15.00. On the right hand side we can quickly add this plus that. So 14.003 minus 15.00. So we have negative 0.997x. On the left, 14.007 minus 15. We have negative 0.993 equal to negative 0.997. So divide by 0.997 on both sides. So the value of x that I'm getting is equal to 0.99. So I can take it to be 996. So that's the value of my x that I'm getting. So since we have got the value of x, we can try to look at what we had. Let's observe. Now we had noticed that the abundance of carbon 14 was attached to x. Now I said x was divided by 100 because we used x and 1 minus x. So what is that supposed to mean? So we'll have 14. This x is this abundance for carbon 14 or nitrogen 14. So nitrogen 14 therefore by percentage abundance is that value multiplied by 100, which is 99.6%. And then I can go for the other one, nitrogen 15, which is 1 minus x. So look at the value that we have. 1 minus 0.996. So I'm getting 0.004. So multiply that by 100. So 0.4%. So basically, this is how you get to find the relative abundance of the isotopes when they've given you the relative atomic mass. So we've handled both situations, where they've not given us and where they've given us a relative atomic mass. And just for practice, I want you to find the relative atomic mass of chlorine given chlorine 35 and chlorine 37. So this one is 75%, the other one is 25%. So find the relative atomic mass of the chlorine atom. Okay, we are just going to talk about them more and look at how we get to calculate them more, how we get to calculate the number of particles, be it the number of molecules, the number of atoms. Okay, so what is a mole? A mole is basically the amount of a substance of a system that contains as many elementary entities as there are atoms in 12 grams of carbon 12. Okay, so each time you're talking about a mole, you're talking about the amount of a substance that contains as many elementary entities as there are atoms in 12 grams of carbon 12. Okay, so basically that is our formal definition of a mole. Okay, so now how do we get to calculate the number of moles? So when we look at our periodic table, we said we have relative atomic masses on our periodic table. For example, if you talk about oxygen, it has got a relative atomic mass of something like 15.994, right? That's what we said. And then if you talk about carbon, we said it has got 12.01, right? So those are relative atomic masses of oxygen and carbon respectively. So the relative atomic mass is going to be referred as the molar mass. Okay, so each time we are determining the number of moles, the number of moles is going to be given as the mass divided by the molar mass. Okay, so this formula can change to mass, relative molecular mass in a case where you are talking about a molecule. It can also be mass over relative formula mass when you're talking about a compound. So all the same, the mass is always going to be on top. Okay, so if I give you to say determine the number of moles, right, in, let's say, 2 grams of carbon dioxide, for the sake of an example. So you look at carbon dioxide. Carbon dioxide is a molecule, so you're supposed to determine the relative molecular mass of carbon by adding, carbon has got 12.01 as its molar mass, and there's only a single carbon in carbon dioxide. And then we've got 2 oxygen atoms, which each has got 15.994, right? So you get to evaluate the two values. So 15.994 times 2 get 31.988. So you get to add the two to get the relative molecular mass. So plus 12.01. So it's something like 43.998. So the units for relative molecular mass or molar mass, it's grams per mole. So 43.998 grams per mole. This is the molar mass that we found for our carbon dioxide. Now we are given to say we're at 2 grams, right? We're at 2 grams of carbon dioxide. So how do we get to find the number of moles? So what we'll say is, we want our mole to be on top, right? So we can exchange this. Whatever is on top will go down. So you basically have a mole. So you have 1 mole of a carbon, or carbon dioxide, sorry. 1 mole of carbon dioxide, there is exactly 43.998 grams, multiplying by 2 grams. So I'm using dimension analysis to determine the number of moles. So in this case, the grams will be able to cancel. Of course, we are talking about the grams of carbon dioxide. So we'll cancel. Basically, what is cancelling are the units. Grams. So you end up dividing, which takes us to our formula where we are saying our number of moles is mass over molar mass, because that's exactly what we are doing. Our molar mass is this one. We are dividing it into what? The mass. So if you get to divide, your answer is going to be 0.045 moles of carbon dioxide. So that's how easy it is to calculate the number of moles. Now looking at our interesting examples, how we get to determine the number of atoms and molecules. So how many copper atoms are in 5.00 grams of copper wire? So the interesting fact is each time they want to determine any number, it may be atoms, it may be molecules, we use what we call the Avogadro's number. So the Avogadro's number is a very common number that I believe each one of us has been exposed to. So that's the number. So the units are per mole. What that means is whatever you are dealing with should be per mole. So in this case we are dealing with atoms. So the units of Avogadro's constant will be atoms per what? Per mole. If we were dealing with molecules, the units were going to be molecules per mole. So it is flexible. That is what the Avogadro's number is. But mole is always going to be there. Now in this case, I want us to determine the number of copper atoms that are in 5 grams of copper wire. So we can clearly see that if we are to find the number of atoms, all we need to do is do away with the mole that is on the bottom. And we can only do that by multiplying by the number of moles. So therefore, we need to find the number of moles of our copper wire. Okay. So how exactly are we going to do that? So let me just create some space. Okay, so we can quickly do that. So our copper has got 63.55 grams per mole as its molar mass. Now I want to find the number of moles. We'd have to write it in another way. So the mole is supposed to be on top, mole of copper, and then we put 63.55 grams, so that we divide it into the 5.00 grams of copper. So we are dividing the mass of copper by its molar mass, so that we get the number of moles of copper. So the grams will go. So 5 divided by 63.55. So approximately I'm getting the number of moles of copper to be 0.078678.2. So those are the moles of copper. Moles. So the moles will basically cancel out, so that you remain with a number of what? The number of atoms. So multiply by the Avogadro's number. What answer do you expect to get? So I'm getting a value of 4.74 times 10 to the power 22 atoms of copper. So that's basically how you get to handle this question. So whether we put molecules, you handle the question the same way. Now feel free to try out the next question on the bottom. The second question says a liter of air contains that number of moles. So we've given us the number of moles. What is the mass of the argon in a liter of air? So how do you get to handle this question? They've given you the number of moles, and then they've given you, and then they want you to find the mass of the argon that is contained in that liter. What do you do? So we basically know that the number of moles is given as mass over molar mass. Not so. So we basically use the same principle to get to find our mass. So number of moles is equal to mass over molar mass. So if you decide to make the mass a subject, it will be mass is equal to the product of number of moles times the molar mass. So the number of moles, ladies and gentlemen, has already been given to be 9.2 times 10 to the power negative 4, which is moles. Molar mass, if you check your periodic table, you find that argon has got a molar mass of 39.95 grams per mole. So the units are going to cancel out. The moles will cancel out, so that you basically get to remain with the grams on top. So I'm multiplying that by that. So approximately I have 0.03675 grams. So if we are to leave our answer to two significant figures according to our question, we would consider 3 and 6. 3 and 6, which would be 0.037 grams. So that's it for this question. And then finally, how many C4H10 molecules are contained in 9.213 grams of this compound, and how many hydrogen atoms are also contained? So feel free to try out this question from what you've learned so far. Okay, so we basically understand that at this point, each time we are determining any number of particles, it may be molecules, it may be atoms, we basically get to work with the Avogadro's constant, which is 6.022 times 10 to the power 23. In this case, where the units are going to be molecules per mole. Okay, so we want to multiply by what? The number of moles, of course. So we'd have to find the relative molecular mass. So look at C4H10, right? So we have 10 hydrogen atoms, each has got about 1.008 grams per mole. Carbon, we have got 4, each has got about 12.01 according to the periodic table. So we're trying to find the relative formula mass or relative molecular mass, whatever you can call it. So 10 times 1.008 plus 4 times 12.01. So if we get to add the two, we have 58.12 grams per mole. So that's our molar mass. So if we have our molar mass, we should be able to find the number of moles since we have our mass. So we said the number of moles is the mass, which is 9.213, divided by what? Divided by the molar mass. So mole over 58.12 grams. So we are dividing. So 9.213 divided by 58.12. Our answer is 0.15885 moles. So we have our number of moles. So 0.1585 mole. Okay, so we are good to go. So we can multiply the number of moles with our Avogadro's constants now to get the number of molecules. So the answer that I'm getting is 9.546 times 10 to the power 22 molecules of what? C4H10. Okay, now the second part of the question is very interesting. How many hydrogen atoms? Very, very interesting. Now you ask yourself, we have this number of molecules of C4H10. Now, in each molecule of the C4H10, of course, if you're talking about the C4H10, we are talking about butane. So what exactly do we have there? We have 10 hydrogen atoms in each. Okay? In each molecule, we have 10. So how about this number of molecules? How many are we going to have? So we end up multiplying by 10. So if in each mole, if in a single molecule, we have 10 hydrogens, how about this number? So it will be multiplied by 10, which will just be 9.546 times 10 to the power 23 hydrogen atoms. Let's talk about the limiting reagent, also known as the limiting reactant. So get a notebook, pause the video, and then try to write out the definition of a limiting reagent, or just pay attention attentively. But I would advise each time you're watching a video, you get a book and then write down and try to attempt some of the questions. Okay, so what is a limiting reagent? So a limiting reagent is basically a reactant that finishes faster in a chemical reaction. Okay, so we can also define the limiting reagent to be a reactant that produces less of a product. Okay, so we can look at the reaction that we have. If we're having a reaction between hydrogen and nitrogen, the one that is going to finish faster is what we call the limiting reagent. Okay, so why do we call it the limiting reagent? We call it the limiting reagent because it is the one that is basically limiting how much of the product is produced. Okay, so think of you having let's say sugar, right? Let's say you have 1 kg of sugar or even 2 kg, and then you just have like a cup of water. So a cup of water that you have is going to limit the amount of the glucose or vesicle that you're going to make. Okay, so that is what we're calling the limiting reagent. It is going to limit how much you can make. That's what we are saying. So equally, when you look at this reaction, whatever is going to finish faster between the two reactants is what we are calling the limiting reagent. The other one is called the excess because it is what is left over after a reaction. So if I ask you to define an excess reagent, it is the reagent or the reactant that remains unused or unfinished at the end of a chemical reaction. The limiting reagent, on the other hand, finishes completely while the other one remains. Okay, so now that we know what a limiting reagent is and what an excess reagent is, we can now move on to understand basically what we're trying to say. So let's try to assume we have 2 moles of hydrogen and then 2 moles of nitrogen in a reaction. Which one is the excess and which one is limiting? So we'll try to determine first of all. So each time you're trying to determine the limiting reagent, it is very important that you get to determine the number of moles. In this example, I'm using moles, but in most of the cases, they are going to give you, let's say they give you 20 grams of both hydrogen and nitrogen are reacting. So now it is up to you to use the 20 grams and then get the hydrogen, which is H2, ignore the coefficients, and then find the number of moles of each. And then you try to make a decision from there. Okay, so now the basic idea is you don't get to determine the limiting reagent by looking at the one having the least number of moles. No, that's not the way it works. So I'll get the hydrogen and compare it against our product. Okay, so we can say that if we compare our hydrogen to our ammonia which is being produced, they are in the ratio of 3 to 2. So I'll try to get the number of moles of my hydrogen. I'll put it there, and then I'll try to find how many moles of the ammonia are going to be produced. So if we cross and multiply there, we're going to have 3x being equal to a 4. So our value of x is going to be 4 divided by 3, which is the 1.33. So those are the number of moles of our ammonia that are going to be produced. Do the same. Compare now the other reactant, which is nitrogen. Nitrogen against the ammonia. These guys are in the ratio of 1 to 2. And then we now have 2 moles. How many do we expect to produce? So if you cross and multiply, your x is directly going to be equal to a 4. So 2 moles of nitrogen are producing 4 moles of that. and then 2 moles of the hydrogen are producing 1.33 moles. So which one is producing more? So the nitrogen is producing more moles, and then the hydrogen is producing lesser moles. So the one that is producing less is what we call the limiting reagent. Okay. So in the actual sense, if we get to react 2 moles of hydrogen and 2 moles of nitrogen, what is going to be produced is what? In case a question asks you to say how much is going to be produced, how many moles of ammonia are going to be produced, we always go for the limiting one. Okay. So in this case, the answer would be 1.33 moles of ammonia are going to be produced. Okay. So that implies that despite us having the nitrogen which is capable of producing a lot of moles, it is not going to entirely react because there is not enough of the other reactant. I think that is the simplest explanation I can give. So there can be questions arising to say, determine the number of moles of the excess reagent that had reacted, all those questions. So in that regard, you'd have to compare the reactants. So the limiting reagent has been determined to be hydrogen. So use the hydrogen, compare it against the other reactant, which is nitrogen. Now you realize that these guys are in the ratio of 3 to 1, right? So 3 to 1. So how many moles of hydrogen did we have? 2 moles. Determine the number of moles of the nitrogen that were in excess. So if you get to cross and multiply there, you're going to have 3x being equal to 2, and then 2 divided by 3, so we have 0.67. So 0.67 are the number of moles of nitrogen that had reacted. So x is representing the number of moles of nitrogen that had reacted with 2 moles of hydrogen. So what this means is, when you get to react 2 moles of nitrogen and hydrogen, the 2 moles of hydrogen is going to finish by only reacting with a 0.67. So meaning that from the 2 moles of nitrogen available, only 0.67 is going to be used. And that's why we are saying from there, the products will stop being formed because the other reactant has been depleted. So that's why we use what finishes to predict the amount of the products and not what is excess, because in the actual sense, not the entire 2 moles of nitrogen are going to take part in the reaction. So if we get to subtract what had reacted by using the limiting reagent, and we subtract from what was available, that gives us now what was in excess. So that's what was in excess. 1.33 moles of our nitrogen was in excess. Now, I want you to look at this question and try to attempt it. Calculate the mass of magnesium oxide if possible. Not if possible. Calculate the mass of magnesium oxide possible if 2.40 grams of magnesium reacts with 10 grams of oxygen. So it's very necessary, very important each time you have a reaction, make sure you balance the equation. So make sure if given you an equation, make sure you observe what is there. So we have 1 magnesium on the left, we have 1 on the right as well. Oxygen, we have got 1 on the left, we have 2. So we can put a 2 there to balance the oxygen atoms, and then we'd have to put a 2 again on the magnesium to balance the number of magnesium atoms, and we've balanced the equation now. Okay, so what do we say? We need to find the mass of magnesium oxide that is going to be produced in this reaction. So we've been given to say oxygen is 10 grams, magnesium is 2.40 grams according to the question. So if you've not done yet so, feel free to pause and then try to find the mass. Okay, so if you look at this question, what exactly are you able to say? You are capable of finding the number of moles, right? It's possible for you to find the number of moles of both magnesium and oxygen. So now, do well to check your periodic table. check your periodic table and basically see the molar mass of both magnesium and oxygen. So of course oxygen we know it's 15.994, and then what do we know about magnesium? Magnesium is 24.31. Okay, so basically go by that. So we can determine the number of moles of magnesium. Number of moles of magnesium is going to be given as a mass over its molar mass. So the mass is 2.40 grams, and then we'll try by the number of molar mass. We are dividing by the molar mass, which is 24.31. So 24.31 grams per mole. So what are you going to get there? 2.40 divided by 24.31. So approximately I'm getting 0.0987 moles. So we have a number of moles of magnesium. Now we can also find the number of moles of oxygen. So equally we'll do the same. The mass of oxygen was given to be 10 grams. Now we'd have to divide by the molar mass. Now each time you are determining the number of moles, whenever you have something diatomic or you're having a subscript, it is considered in determining the relative molecular mass. So, but we don't consider the coefficients. We ignore the coefficients as seen in magnesium, but we are considering the subscripts. If we add the 3 on magnesium, we'll do the same, but in this case, we have only a coefficient. We don't consider the coefficients of the mole ratios. So we'd have to multiply by 2. So the 2 multiplied by the 15.994 over oxygen, which our approximate will be 31.988, which is just like 32 grams per mole. So I get to divide that. So our number of moles over oxygen, 0.3126 moles of our diatomic oxygen with a subscript 2. So now, which one is limiting in between the two? Is it oxygen or magnesium? Which one is the limiting reagent? So we've calculated the number of moles, right? We've calculated the number of moles. So we can try to use the number of moles and determine how many moles are to be produced. Okay. So let's assume this question was general, where they had asked us to say find the limiting reagent. In that case, we'll look at what we have. So let me just try to move this one here so that we can work with it. Okay, can move it there. Okay, so we have our oxygen there. These are a number of moles of our oxygen. So we know these guys are in the ratio of 2 to 1, right? So of course I've swapped them. This is magnesium. So magnesium has got a stoichiometric coefficient of a 2. Oxygen has got a stoichiometric coefficient of a 1. So if you get to divide them into their values, what do you expect to have? So on this side of oxygen, the number of moles remain the same. And then on the magnesium part, 0.0987 divided by 2. So that would be 0.04935. So which one is bigger? So the one that is bigger is in excess, the one that is smaller is limiting. So we can clearly see that the number of moles of magnesium after dividing by their mole ratios is actually smaller. So in this case we can conclude to say it's a limiting reagent. What is the shortcut in terms of determining which one is the limiting reagent? Okay. So you now know how to determine the limiting reagent by using the mole ratios and the number of moles. Now, in this case, we know that since we've found our limiting reagent, we're supposed to use our limiting reagent to determine the product. So use the mole ratios. Now, in this case, we'll assume we've not found the limiting reagent. We've not found the limiting reagent. We're just going direct. So we can do it by two ways. First of all, we'll consider the same magnesium. So magnesium compared to our magnesium oxide, these two guys are in the ratio of they're in the ratio of 2 to 2, which implies that they're in the ratio of 1 to 1. So magnesium compared to magnesium oxide, they are in the ratio of 2 to 2, which is just like 1 to 1. So when two reactants products or a reactant and a product are in the ratio of 1 to 1, it tells us to say that they have got the same number of moles. So the number of moles that we've determined of magnesium are exactly the number of moles of magnesium oxide that can be expected. So therefore, the same number of magnesium that we have for the number of moles is the same number of moles of magnesium oxide. So therefore, we have the number of moles of magnesium oxide already. And then you know how to find the mass, right? We know the number of moles is mass over molar mass. So you can find the mass as the product of the number of moles and the molar mass. So how do you find the molar mass? We have, of course, I said ignore the stoichiometry coefficient. So our magnesium is 24.31, and then plus oxygen, which is 15.994, right? So our answer for the molar mass is approximately 40.3. So our mass is obviously going to be a product of the number of moles and the molar mass. So I'll go direct. I'll multiply the two. The molar mass I've told you to say, I've found 40.304. The units are grams per mole. So multiply directly number of moles times molar mass to give you the mass. So our mass, which is the product of the number of moles and molar mass, will give us 0.0987 multiplied by our molar mass. The mass is 3.978 grams. Okay, so what's the mass if we are to use magnesium? Now let's try to consider oxygen. In this case, we are assuming we didn't know what was limiting. So equally for oxygen, compare oxygen against magnesium oxide. These guys are in the ratio of what? So oxygen, there's a coefficient of a 1. For magnesium oxide, there's a 2. So we are in the ratio of 1 to 2. So if we have 0.3126, how many moles of magnesium oxide do we expect? I've put X to represent that. So in this case, they are supposed to be doubled. So the number of moles would be 0.6252. So using those number of moles, you can multiply them against the molar mass as well. So after multiplying by the molar mass against the number of moles that are expected by using oxygen, the expected mass is 25.198 grams, which is like wrong. Okay, so we can't use oxygen because it is going to give us what is not true. It was in excess. Not every amount of oxygen reacted in the reaction, because our limiting reagent was our magnesium, as earlier predicted by the mole ratios. So always whenever we want you to determine the amount of a product that was produced, we get to use the limiting reagent. The limiting reagent concept is very, very necessary and very important in the study of stoichiometry and our chemistry in general. So just some quick few points that you would need to get is in this case, if the question had asked us to determine how much of the oxygen was left over after the reaction, in that case, knowing that we've determined our magnesium to be limiting, we can use the mole ratios between magnesium and our oxygen to determine how many moles of oxygen are basically reacted in the actual reaction. So you find that these guys are in the ratio of 2 to 1. So now that magnesium is limiting, we can get this number of moles to use it to determine the number of moles of oxygen that actually reacted. So the value of x that you're going to get represents the number of moles of oxygen that reacted. And then this is what is reacted. Now notice that in the question they've also given you the mass of oxygen, which we had used to find the number of moles. So that number of moles of oxygen that you can find using 10 grams is what was available. So subtract from what was available, remove how much had reacted. It gives you the number of moles that were left over or in excess. So you can use the number of moles that were in excess and the relative molecular mass of your oxygen molecule to find the mass that was left over after the reaction. So let's go over combustion analysis. So what is combustion analysis? So this is a method that we basically get to use to determine the empirical formula of a compound that contains carbon and hydrogen. So it involves burning the compound in excess oxygen to produce carbon dioxide and water. An example we can have is if you have CH, which is a hydrocarbon, burning in excess oxygen to give you carbon dioxide and water. You may also have other products depending on the compound that you are burning. So the key things to note are the oxygen should be in excess, and then this compound you should know its constituents or composition, know the composition of like what elements are making up that compound. And then before they start, you need to weigh the mass. So the mass should also be known. The mass of that compound should be known. So after burning the compound in oxygen, you have the mass of carbon dioxide and water. So you should be able to find the exact number of carbon and hydrogen contained in the compound. That is what combustion analysis is concerned about. So we basically get to work with the ratios. So if you look at carbon dioxide can help us by using the ratios of the carbon atom to carbon dioxide. We know that in carbon dioxide we have a single carbon and then we have carbon dioxide. So you multiply that against the mass of carbon dioxide. Let's say the mass was 10 grams. So put the molar mass of carbon and then put the relative molecular mass of carbon dioxide. You'll be able to get the mass of carbon because you are using a ratio. Equally, if you go to water, there are 2 hydrogen atoms contained there. So you say 2 hydrogen atoms over the water molecule multiplied by the mass. Let's say the mass was 8 grams. So you'll be able to find the mass of carbon and also the mass of hydrogen respectively using the 2. Now after you get the 2 masses of carbon and hydrogen, if we had a substance or a compound containing oxygen, for us to find the mass of oxygen, we would have to add carbon and hydrogen and then subtract from the total mass of what? Oxygen. You'll be able to get, or from the total mass of a compound, you'll be able to get the mass of your oxygen atom. Okay, so with that in mind, after you now have the masses of carbon, hydrogen and oxygen, we do know that after having their masses, we are able to use their molar masses from the periodic table and determine their number of moles. And from there, after you have the number of moles, I believe we know that we are supposed to divide by the least number of moles, and then you get the ratios. What you're going to have is what you call the empirical formula, and that is the basic idea of this method. So let's look at a few examples, just 2 examples to help us understand more. So a hydrocarbon fuel is fully combusted. That is our question 1. So question 1 says a hydrocarbon fuel is fully combusted with 18.214 grams of oxygen to yield 23.118 grams of carbon dioxide and 4.729 grams of water. Find the empirical formula for the hydrocarbon. So a hydrocarbon is a compound that is made up of hydrogen and carbon only. So we know we are burning a hydrocarbon, which is CH. So is fully combusted. So In case they ask you a question to say, why do we burn the compound in excess oxygen during combustion analysis? So the basic idea is that you want the entire compound to be fully combusted or to be completely used up, so that as you get to look at the other side of the formula where you have carbon dioxide and water, you want to make sure that every amount of carbon that was present there is exactly what is in the carbon dioxide, and every amount of hydrogen that was available is exactly what is in water. That's why we are saying it should be fully combusted, so that every carbon appears on the product side and every hydrogen as well. So this is the reaction that we have. We're burning our CH, which is the hydrocarbon, in oxygen to give us carbon dioxide and water. Now what are they saying? So hydrocarbon fuel is combusted with 18.214 grams of oxygen to yield 23.118 of carbon dioxide and 4.729 grams of water. Okay, so we are interested in the mass of carbon dioxide and water. So that of carbon dioxide has been given to be 23, right? So take note of that, 23.118 grams of carbon dioxide. And then of water, we are told it's 4.729. So I hope you're able to remember what I told you earlier. So from our explanations, we said, look at carbon dioxide, come up with a ratio of carbon to carbon dioxide. So you have a single carbon atom in carbon dioxide. Multiply against the mass. So our mass is 23.118 grams. So what we are going to get is the mass of carbon contained in the compound. So we can do that. So look at what we have. If you go to your periodic table, you realize that the molar mass of carbon is 12.01, and then for oxygen it is 15.994, which is like 16 approximately. So let's try to find the molar mass, relative molecular mass of carbon dioxide. So you'd have to look at that. So you have a single carbon atom, and then you have got two oxygen atoms, so you'd have to multiply by 2. For carbon, it's just a single one. So 12.01 times 1 is 12.01 plus 2 times 15.994. So I can say approximately we have like 44 grams per mole as the molar mass of our carbon dioxide. So we can substitute now. Well, on the bottom where we have carbon dioxide, we put 44 grams per mole. On top where there is just a carbon, we put 12.01 because that is the molar mass of our carbon from our periodic table. Now you realize that the units are the same, so the grams per mole cancel out. So you remain with 12.01 basically divided by 44 times 23.118. So the mass is approximately 6.31 grams of carbon dioxide. Okay, that's for the first part. So let's consider for significant figures. I can put a 0 here. Going to the other part for water, we'll basically do the same. So we do understand that in water we have got two hydrogen atoms, right? Short by the subscript of a 2. And then we get to divide by the water molecule itself, and then we multiply by the given mass, right? So we'll do the same. Now, one thing that we understand is hydrogen on the periodic table has 1.008 grams per mole. Oxygen has got 15.994. So we'll basically perform the calculations. We have got 2 of those. Oxygen is just a single one. So if you get to add What is the relative molecular mass of water? I believe we approximately know that is 16 grams per mole, right? If you get to add 15.994 plus 2.16016, you basically get 18 grams per mole. So you can substitute that. So we have water, we'll put the relative molecular mass of water, which is 18 grams per mole. And then where we have 2 times hydrogen, our hydrogen is 1.008. So 2 times 1.008 divided by 18, multiply against the 4.729. The answer that I'm getting is 0.5296 grams. So what is our mass of what? Yeah, what is our mass that we have? Our mass of water, right? Or our mass of hydrogen, sorry. Okay, so this is our carbon, that is our hydrogen. Now we need to find the mass of okay, so basically if you look at this compound, I know in my mind I'm still thinking of a compound that is made up of both of including oxygen, where there's oxygen there, but in this case there's just carbon and hydrogen, so we are done. If we had oxygen, we were supposed to be given the mass of the compound, so that we add the two, carbon and hydrogen, and then we subtract from the total compound to get that mass of the oxygen atom. Okay, but in this case there's no oxygen, so we just get to use a 2. Okay, so that equation is no longer important to us. So we have our carbon and our hydrogen. So this explains how we go about empirical formula determination in a case where they've already given us a mass. So that's exactly the procedure that we're going to follow here. Okay, so we have 0.5296 grams. So whenever you have the masses of the elements or the atoms, just get to divide now by the molar mass. So divide by the molar mass so that you get what? The number of moles. So you're just getting these values from your periodic table. So I'll start from the right hand side since I already have a value on the calculator. So I'm getting 0.5254. I'll do that again. 0.5296 divided by 1.008. 0.5254. Okay, it's the same. And then I'll do the same on the carbon. 6.310 divided by 12.01. So 0.5254 to significant figures. So you always get to divide by the least number of significant figures, by the least number of moles. Yeah. So in this case, the least number of significant figures. I don't know why I'm making a lot of these mistakes, but we are dividing by the least number of moles. So in this case, the values are just the same. So if one of them was smaller, we are going to divide by the smaller one. But in this case, they are the same. So we just get the same value and divide. So we realize that these guys are in the ratio of 1 to 1. No two ways about it. So therefore, since we have a ratio of 1 to 1, after dividing, our answer is CH. This is now the empirical formula of that compound. Okay, so question 2 says a compound with a known molecular weight, which is the molar mass, has been given in the brackets, that contains carbon, hydrogen, and chlorine was studied by combustion analysis. When a 0.367 gram sample was combusted, 0.659 grams of carbon dioxide and 0.0892 grams of water formed. What are the empirical and molecular formulas? the compound. So quickly, we are told it contains carbon, hydrogen, and what? Chlorine, right? So write that. Carbon, hydrogen, and chlorine. We don't know the ratio that they're existing, which is the empirical formula. So burning it in oxygen, what was produced was carbon dioxide, okay, and water. Of course, we realized that there was also production of chlorine, right? Chlorine was also produced. Now, if you pay attention to this question, what information have they given us? They have not given us the amount of chlorine that was produced, so don't worry much about that. Don't worry about it. Okay, so the key information is we've been given the mass of a sample, which has been given to be 0.367 grams. Carbon dioxide, the mass has been given to be 0.659 grams. Water has been given to be 0.0892. So it's very important each time you're answering these questions, you come up with the data and just get it, have it at your fingertips. Okay, so we'll start first of all by focusing on our carbon dioxide, just like from our previous question. Ratio, carbon over carbon dioxide, right, times the mass, 0.659 grams, to get the mass of our carbon. So carbon, we said the molar mass is 12.01. We said the relative molecular mass of carbon dioxide was what? 44 grams. Of course, grams per mole. Grams per mole. So 12.01 divided by 44 multiplied by 0.659. I'm getting a value of 0.1798. I can put one more value, 8. So we have 5 significant figures. So what is our mass of carbon in the carbon dioxide, which is the same as the mass of the carbon in the what? In the compound. We'll go to water now. So for water, we have got 2 hydrogen atoms, and then we have water itself multiplied by the mass. So quickly, we'll just substitute. We know hydrogen is 1.008, right, from our periodic table. And then water itself is what? 18 grams per mole. So 2 times 1.008 divided by 18 times 0.0892. So here what we are getting is a very small value of 9.9904 times 10 to the power negative 3 grams. So we now have the mass of both hydrogen and carbon. Okay, we can clear some space now. Okay, so now notice that the question was emphasizing to say it contained only, the compound only contained carbon, hydrogen, and chlorine, just like I've indicated there. So if we have the mass of carbon and the mass of hydrogen, and then we have the mass of the whole compound, do you agree that we're able to find the actual mass of the chlorine atom, which is the only missing one, by subtracting? So we do know that the addition of carbon plus hydrogen plus chlorine masses are supposed to give us what? The total mass of 0.367 grams. Right? So for our carbon, we have 0.17988. For hydrogen, we have 9.9904 times 10 to the power negative 3 plus chlorine, which is supposed to be equal to 0.367. So quickly add what we have. So what I'm getting is after adding the two, I'm getting a value of 0.1898704. So if we get that value and take it on the other side to subtract from the total mass, our chlorine mass minus what we have calculated, sorry, yeah, our total compound mass minus the calculated summation of carbon and hydrogen should be subtracted. So if we get to subtract 0.367 subtracted by the summation of carbon and hydrogen, the missing mass of our chlorine is 0.17712. Sorry, 3 to 5 significant figures. So we've now determined the mass of all the 3 atoms or elements that were contained in our compound: carbon, hydrogen, and chlorine. So we can now indicate their masses. For carbon, 0.17988 grams. Hydrogen, 9.9904 times 10 to the power negative 3 grams. Chlorine, 0.17, write that again, 0.17713 grams. So since we have the masses, what are we capable of doing? We are now capable of determining the number of moles. How do we get to determine the number of moles? By dividing by the molar mass. The molar masses is 12.01 grams per mole. 12 point sorry, hydrogen is 1.008 grams per mole. Chlorine is what? What's the molar mass of chlorine if you check your periodic table? Is it 55? So chlorine molar mass is basically 35.453. Sorry for the delay. Okay, so we can quickly divide to get the number of moles, just like we had done from the previous example. So 0.17988 divided by 12.01, 0.01498 to 4 significant figures. The other one, 9.9904 times 10 to the power negative 3 divided by 1.008, 9.911 times 10 to the power negative 3. Finally, for chlorine, 0.17713 divided by 35.453, 5.005 times 10 to the power negative 3. So for your own information, I would want to remind you guys to say there are some questions where they would give you the percentage composition of the elements. So in such a case, assuming the total mass is 100%, you are able to consider the same percentages as their masses, and then just quickly get to divide by the molar masses to get the number of moles, and then divide by the rest. Okay, so we've determined the number of moles by dividing the calculated number of moles from our combination analysis. We can now divide by the least. Which one is the smallest among these 3? Obviously it's that one, right? So 5.00 times 10 to the power negative 3 is less than 9.911, since we have got the same power. So 5.005, sorry. Yeah. So I'll start from the other side. 0.01498 divided by 5.005 times 10 to the power negative 3. So to 4 significant figures, 2.993. We go to other value, 9.911 times 10 to the power -3 divided by 5.005 times 10 to the power -3. So 1.980. The last one is a 1. So since all these are, as we can see, they are all having 9s before, so they are all having 9s, right? If we get to consider a single number, so that one becomes a 3, this one becomes a 2, and that is remains a 1 in terms of ratios. So the answer that we've gotten in this case is we have got 3 carbon atoms, 2 hydrogen atoms, and a single chlorine atom. So this is what we call the empirical formula. Okay, so we can quickly now find our what we call the molecular formula. So we'll look at this. So we have 3 carbon atoms plus 2 hydrogen atoms plus a chlorine atom. I'll put them in brackets. Multiply by n is equal to, the molar mass is 146.99. Okay, so we can substitute our molar masses there. We know what they are, so I'll just go direct. So for carbon is 12.01, for hydrogen is 1.008, for chlorine is 35.453. So I'll multiply the carbon by 3, the hydrogen by 2. So the answer that I'm getting is 73.499. Of course, we have n outside, which is equal to 146.99. So get to divide 146.99 divided by 73.499. So I'm getting a value of 1.99. So if you get to round off at, we need to make sure our n is always a whole number, so the answer is a 2. So a 2 would have to be multiplied by the empirical formula, which was C3H2Cl, right? Multiply all the subscripts by a 2. So we have 6H4Cl2. This is exactly what the molecular formula is. The molecular formula shows the exact number of atoms contained in the compound, while the empirical formula gives us them in the lowest common ratio. Okay, so we have a question from Stoichiometry that is dealing with titration, and of course the question says the blood alcohol ethanol level can be determined by titrating a sample of blood plasma with so we are titrating first of all a sample of blood plasma with an acidic potassium dichromate solution, resulting in the production of chromium 3 ions and the carbon dioxide, as we can see in the equation. The reaction can be monitored because the dichromate ion is orange in solution and the chromate ion is green. The unbalanced redox reaction is given there. Okay, so now the question says if a volume of 1.05 milliliters of 0.06 molar concentration of potassium dichromate solution is required to titrate 30 grams, determine the mass percent of alcohol in the blood. Okay, so one thing that we need to understand first of all is we have been given blood plasma, as we can see. Okay, so now in the blood plasma, that is where we do have our alcohol, because the question says the blood alcohol level can be determined by titrating a sample of blood plasma. So in the blood plasma, that is where we have our blood alcohol. So the mass that has been given there is the mass of the blood plasma itself. So we'd have to use titration to determine the mass of the alcohol. So this is like being able to determine the purity of the blood plasma, because in the reaction, the potassium dichromate was only reacting with what? With our alcohol. Okay. Now that alcohol is contained in the given mass of our blood plasma. Now, notice that the question says this is an unbalanced equation, so we'd have to balance it first of all. Okay, so looking at what we have, we'd have to use the method that we call ion electron method. So for the sake of this video, we're not going to do that, but in case you don't know how to go about it, basically, you can use the link, the card shown there, or at the end of this video, you'll be able to see the link that is going to guide you on how you get to answer that question. Okay, so how basically do we get to handle that? So just to give you some tips is, you'd have to use the ion electron method. So if you observe this, this is related to the chromium 3 ion. So you have to write it in this way. Chromium 2O7, 2 minus, gives you chromium 3 plus ions. And then the ethanol C2H5OH is related to carbon dioxide on the other side. So this is a case where you need now to balance. So the first thing that we get to balance is balance the other atoms other than oxygen and hydrogen. So looking at our first equation, we have to balance the number of chromium ions. So add the 2 there. And then notice that we have got 7 oxygen atoms. So we have to add 7 water molecules. So if you don't know how to go about this method, please watch the video given. The link is given on top there. Alright. So for the sake of this video, I will not do that, but I'll just give you a balanced equation of this equation in advance. So the balanced form of this equation is 16H plus 2 chromium O7 2 minus plus C2H5OH, giving us 4 chromium 3 plus 11 water molecules plus 2 carbon dioxide molecules. Okay, so for the sake of this video, again, I do emphasize to say we are interested in determining the mole ratios between chromium against our ethanol. So basically notice that they are in the ratio of 2 to 1. So the other information is not necessary, it is not important. Okay. Now let's begin answering our question. So the information that we've been given about our titration is we've been given 1.05 as our volume. So each time we're dealing with more calculations, we'd have to have that answer in liters. So let's quickly convert that to liters. So that 1.05 is supposed to be divided by 1,000 for it to become in liters, because 1,000 milliliters make up a liter. So that 1.05 divided by 1,000. So the answer in liters becomes 0.03105. So we have our volume in liters. The concentration has already been given in molar concentration, which is 0.06 molar concentration. So look at this information. This information is for the potassium dichromate, which is this one, okay, which we've already balanced. So we should be able to determine the number of moles of our potassium dichromate that were used to titrate the 30 grams of the blood plasma. Okay, so all in all, we do basically understand that concentration gives you the number of moles dissolved in a volume, right? So for us to find the number of moles, we'd have to multiply the concentration, which is 0.06. Molar concentrations means mole per liter. Now we're multiplying against what? The volume, because number of moles is equal to concentration multiplied by volume. The volume is 0.03105 liters, right? So we can quickly do that. Liters would have to cancel out. So we're now multiplying that. 0.06 multiplied by 0.03105, so that we get our number of moles. So the number of moles that I'm basically getting are, so number of moles of our potassium dichromate from the information given, I have 1.863 times 10 to the power negative 3 moles. Okay. So now that we have a number of moles of our potassium dichromate, we are supposed to use the mole ratios between our chromate, dichromate, potassium dichromate, and our ethanol. So now these guys are in the ratio of 2 to 1. So every 2 moles of potassium dichromate, there is a mole of the ethanol. So we'd have to cross and multiply there. So you notice that if you have 2 moles of potassium dichromate, you have a single mole. So it's like it is becoming halved. So if we are to find the value of x, we'll notice that it's going to be the calculated number of moles divided by 2. Or if you, so you have 2x in short, giving us 1.863 times 10 to the power negative 3. So for you to find the value of x, you'd have to divide by 2. So the number of moles of the ethanol that had reacted is 9.315 times 10 to the power negative 4. So we found the number of moles. That is for C2H5OH. Remember the one that we had determined was for potassium dichromate first of all. Okay. Now, looking at our question, if we look at our question, in our question we are given the mass of the blood. Okay. So now we found the number of moles of our ethanol there. So if we have the number of moles of our ethanol, we should be able to find what? Its mass, right? So that we can find its mass percentage contained in the blood. So first of all, we need to find the molar mass, since we already have calculated the number of moles. So what is the molar mass of ethanol? So how do we calculate the relative molecular mass? So we do know that C2H5OH is the formula that we have of our alcohol. So just begin calculating their molar masses. So carbon has got a molar mass of 12.01, and there are 2 in this case. I'll go again to hydrogens, 5 hydrogens. Each has got 1.008 times 5. Oxygen is a single one, 15.998, 15.94 times 1. And then finally we have another oxygen, or another hydrogen. So whatever you get there, you need to add for you to get what we call the relative molecular mass. So for me, what I'm getting as my relative molecular mass of ethanol is basically 46.07 grams per mole. So we have our number of moles, and then we also have our relative molecular mass. So we're able to find the mass. Remember, we said number of moles is given by the mass divided by the molar mass. Now in this case, we want to find our mass. So our mass becomes a product of our molecular mass, or our molar mass, 46.07 grams per mole. We are multiplying it against the 9.315 times 10 to the power negative 4 moles. Okay. So at this point, we'll be able to see that we're able to find the mass. So what mass are we getting after multiplying? So we have 9.315 times 10 to the power negative 4 multiplying by 46.07. So the mass I'm getting is 0.042914 grams. So we have our mass of our ethanol, okay, that had reacted with the given information of our potassium dichromate solution. So how do we get to find the mass percent of the alcohol in the blood? So this is for the alcohol ethanol from the equation. So we are given the mass 30 grams of the mass of blood. So how do we get to find the mass percent? So we'd have to use 0.042914 grams divided by 30 grams itself times 100. Now notice that the grams are going to cancel out. So we divide that by 30 times 100. So the answer that I'm getting is 0.143%. Okay, so if you look at the piece of information that we were given, so we had a minimum of 3 significant figures. So this is okay as our final answer, 0.143%. That is the mass percent of our alcohol in the blood. Okay, so if you still don't know how to go about the balancing of the equation, watch this video short here. Okay, so in this video we just want to balance the given equation there. Okay, so basically we know how we basically get to balance simple equations. For example, if you look at the other process where we have nitrogen and hydrogen reacting to basically give us ammonia. What basically happens is here, this is kind of an equation we're able to balance it by observation, where you observe, okay, to say, okay, I can carry it to say, if I check my left hand side, I've got 3 hydrogen atoms. On my right hand side, I've got 2. What do? I'll basically tend to multiply by 3 over 2, right? And then I multiply the entire equation by 2. So after multiplying the entire equation by 2, we realize that we're going to have a 2 there and a 2 there. And then ultimately you observe that the equation is balanced. Now, look at this equation that we have. If you try to observe what we have, you'll not be able to balance it by observation. Okay. Why, for example, we can see that we don't have even oxygen on the right hand side. So we use what we call the ion electron method, where we need to split the reaction into half reactions. So quickly we'd have to see that we only have a single product there, right? So all these reactants are going to be split into half. So we'll start with the first reactant to write it, right? So we have, I'll write it as it is. So our first reactant, we have IO3 minus. So we relate it to our own product, which is I2. As we go to the second one, I'll get the other reactant as well. I'll also relate it to what? To our own product. So this only happens when you only have a single product. In cases where we've got different products, we realize that we'd have to look at which one is more related to the product, right? So basically that's how we get to consider that. In this case, now that you've come up with the 2 half reactions, this is called, of course, a redox reaction because we have an oxidation reaction and also reduction reaction. So we'll be able to identify that as we get to proceed. So using the half reaction method or the ion electron method, the first thing that you're going to do is, first of all, you need to balance the other atoms other than oxygen and hydrogen. So oxygen and hydrogen basically are the main things that we get to focus on. But before we could get to balance our oxygen and our hydrogen, we'd have to balance other atoms. So I'll start with, first of all, the first half reaction, which is this one. Now, observing the only other reactants or the only other atoms that we have other than oxygen and hydrogen, we have iodine. Now observe iodine. We have got 2 on the right hand side, we have 1 on the left. So we'd have to add a 2 on what? On our left hand side. So we've balanced the number of iodine atoms. Proceeding to the second one. Equally, we observe that we have 1 on the left and then we have 2 on our right hand side. So equally, we would have to add a 2. So we've balanced all the other atoms apart from oxygen and hydrogen. So the second step is to balance oxygen. So we get to balance oxygen by what? So the oxygen is balanced by adding water. We balance hydrogen by adding the hydrogen ions. So we start with oxygen. So we'll start with first half reaction there. We can clearly see that we've got 6 oxygen atoms. How? I'm multiplying the subscript 3 against the coefficient 2. So we'd have to add 6 water molecules to our right hand side to balance up. So 6 water molecules. Now, one thing that is there is, the moment you introduce water molecules, which is used to balance oxygen atoms, there is need for us to also balance the hydrogen atoms that are introduced because of the water molecule. So how many are they? 6 times 2, they are 12. We'd have to add the hydrogen ions, as we can see on our left hand side. So add 12 hydrogen ions. Okay. We'll go to the secondary half reaction. So the second half reaction, basically, we don't have oxygen and hydrogen. So it's already balanced in terms of the atoms that we have. Okay, cool. So the other thing, after you've balanced the oxygen, the hydrogen, and all the other atoms, this is when now you get to focus now on the charges, right? The charges are now very important. So I'll start with the second half reaction since it is simple. So we have a negative there, we have a coefficient of a 2. So we'll have to multiply the coefficient by the charge. So we can see the overall charge is negative 2 on the left. On the right hand side, there's nothing, there's a 0 there. So we are observing a change from negative 2 to 0. Now, the question that you need to ask yourself is it an increase or reduction? So from negative 2 to 0, we are actually, if you look at your number line, you realize that the negative numbers, as we move towards 0, we are actually increasing. So this is an oxidation reaction. So we use oil and Lig to remember that. Oil is loss, oxidation is loss, and then Lig, reduction, is gain of electrons. So in this case, where we are saying the increase in our oxidation number is oxidation already, so we can clearly see that this is going to be what? loss of electrons. So how many electrons were lost? So we had lost 2 electrons for this to be an oxidation reaction. Now going to our first half reaction, we have 12 positives. So I'll write the 12 positives. We have got a negative here multiplied by the coefficient of 2. So I have a minus 2. So the overall charge becomes what? Positive 10 on the left hand side. On the right hand side, there's a 0, there is a 0. So overall, we have a 0 charge on our right hand side. So we're moving from 10 to 0. The other way you can think about this is, consider the electrons to be negative. So you have 10 there, and then you have 0. So we'd have to add negatives each time on a side so that we get to balance up. Remember what we add here? We add a negative 2, and then we're going to 0. So the question that you need to ask yourself is, where should I subtract for me to be able to get equivalent numbers? So here we had to subtract 2 here. That's why we added 2 electrons. So here, what we're going to do, we need to subtract from the 10. So we'll subtract 10. So that minus 10 is going to represent 10 electrons being gained in our reaction. That is also a smart way of thinking about it. Now at this point, we'd have to balance now the number of electrons in the two half reactions. There we have got 10 electrons, here I've got 2 electrons. So how do we balance? We'd have to multiply this reaction by a 5, right? So a 5 is going to multiply everything in this other half reaction. So clearly you see that the numbers are going to change, right? So where we have a 2, it is going to become what? 10. Where we're multiplying by 5, so it will become 5, and the electrons themselves are going to become now 10, right? 10 electrons. So since they are on the opposite sides, the electrons would have to cancel out. They are being gained and lost. So where they're being lost is in the oxidation reaction. Where they're being gained is in the reduction reaction. So that is what redox is all about. So at this point now, is there anything else that is on the opposite sides? There is nothing. So we can now rewrite the entire equation by starting with, first of all, the oxidation reaction. So we have 10 iodine as our reactant from the second half reaction, and then we have got, I can start with the 12. So we have 12 hydrogen ions, and then we have got 2 IO3 minus. We are done with our reactants. On our product side, we have 5 I2 plus, so there is an I2 there as well. So basically, all in all, we can say we're going to have 6 of them. We can just sum them up. And then what else do we have? So we have 6 water molecules, and then we have I think that's all. Yeah, that's all. We're now done, since we already added 5 plus the one there to give us 6, and then we have got 6 water molecules. Now we can try to make an observation. On the left hand side, you have got 12 hydrogen ions. On the right hand side, 6 times 2 is also 12. How many oxygen atoms do we have? 2 times 3 is 6. 6 times 1 is also 6. The iodines, how many do we have? 6 times 2 is 12. 2 times 1 is 2 plus 10, 12. So we've balanced the entire reaction. And this is basically what ion electron method is all about, also called the half reaction method. Just in summary, first of all, split the given reaction into half reactions, and then balance all the atoms other than oxygen and hydrogen. Then balance oxygen by adding water, balance hydrogen by adding the hydrogen ions, balance the charges, balance the number of electrons, and then combine the half reactions. Okay, so let's try to balance this equation in alkali solution. Okay, so we cannot balance this equation by observation, so we'll have to use what we call the half reaction or the ion electron method, except we are balancing it not in acidic media. So in acidic media, basically we get to end with the proton ions. We're okay reading our final equation with the protons. Now for alkali and basic, basically we'd have to end with hydroxide ions instead. So there's an extra step that you're going to observe. Okay, as usual, our first step is to split the reaction into its half reactions. So we only have a single reactant, so we'd have to relate it to both products. So I'll first of all write the half reactions. So we have manganese O4, 2 minus. I'll relate it first of all to our first product, which is manganese O2. I'll go to the other half reaction. our only reactant, again related to our other what? Products, our second product. So what is the first step? We've now split our given equation into its fractions. What is our next step now? Our next step is to balance all the other atoms before oxygen and hydrogen. So looking at our first half reaction, we only have manganese and oxygen. So we'd have to balance manganese before we balance oxygen. Now we only have a single manganese on both ends, so that is already balanced. So our first step directly is to proceed to now balancing our oxygen atoms, right? How many oxygen atoms do we have? So on the left we have 4, on the right we have 2. How do we get to balance? So we balance the oxygen atoms by adding water, right? So add 2 water molecules. Why am I adding 2 water molecules? Because we have 4 oxygen atoms, here we have 2. So the 2 water molecules will come with 2 oxygen atoms, making it 4 on the right as well. Now, you observe that each time we are balancing oxygen atom, there is an issue now with the hydrogen atom. So we get to balance hydrogen atoms as our next step. So on the right hand side, I'm going to add 2 times 2, 4. So we need to add 4 hydrogen atoms. So at this point we've balanced oxygen, hydrogen and also manganese. We can quickly now go to our second half reaction. For our second half reaction, we'd have to balance first of all, as usual, other atoms other than oxygen and hydrogen. So we have manganese as our only other atoms. So we are already balanced. To oxygen, we have 4. There we also have 4. So that is already balanced. So all the atoms in our second half reaction are already balanced. Oxygen is already balanced, there is no hydrogen, so everything is already balanced. Now after you've balanced all the atoms in both half reactions, you now need to balance the charges in the 2 reactions. So I'll start with a simpler one, which is the second one. So here the charge is -2. So we multiply our charge by the coefficient on the left. Here there is a 1, so the charge remains -2. On the right hand side there's a charge of -1, the coefficient is also a 1. So we have a -1. So now observe, if you look at your number line, you have a 0 there. This side you have positive numbers, this side you have negative numbers. Now if I ask you a question, which one is bigger between -2 and -1, you realize that we're counting going towards the right hand side, right? So clearly -1 is bigger than -2. So this is obviously an increase in our oxidation number, which is oxidation. So use oil and lead to remember that. Oxidation is loss, reduction is gain. Okay, so since oxidation is loss, or the other prototype that I'm using to help you remember is the addition of where can we add electrons so that where can we subtract so that we balance the numbers. So we can subtract from the -1 another negative to make it -2. We are equal, right? So we are adding an electron on our right hand side. So that is an oxidation reaction. If you go to the other one, you also observe here we've got a positive times 4, we've got 4 positives. You have a -2 times the coefficient of a 1, it remains a -2. So that will give us a charge of a +2 on our left. On our right there are zeros, so we just have a charge of a 0. So from 2 to 0, is it an increase or a reduction? It's a reduction straight away. So where can we subtract so that we balance? We can clearly subtract from a positive side to reduce it. So -2. So that means we'd have to add 2 electrons on our right hand side. That is basically how we balance the charges. So I'll add 2 electrons to our left hand side. But before that, let me just create some space. Okay, so we can add how many electrons? We're adding 2 electrons. Okay, so we've balanced the charges in both half reactions. Now the other step is to balance now the number of electrons in both half reactions. So in the first half reaction we've got 2 electrons. In the second one we only have a single electron. So we multiply by what? By a 2. So 2, 2, 2. We've balanced now the 2 half reactions. The number of electrons are going to cancel out. and then the rest are going to be combined to form our final reaction, our final equation. So we can start with a second half reaction. 2 manganese O4 2 minus plus 4 hydrogen ions plus manganese O4 2 minus, giving us on our right hand side manganese O2 plus 2 water molecules plus 2 manganese O4 minus. So I've just combined the reactants that have remained and also our products, and basically that is how we go about balancing of our half reactions, or balancing our given equations, reactions in the alkali of the basic media. Now, have we balanced it in full? No, we've not. Okay, so if it was in acidic media, you can end at this point, but it is not in acidic media. We would have to balance it on what we're calling the basic of the alkali media. So we don't basically, the presence of the hydrogen ions indicates acidicness, so we need to show alkalinity by the presence of the hydroxide ions. So basically what we get to do, our extra step is to add an equivalent number of hydroxide ions on each side. Okay, so we have got 4 hydrogen ions in this case. We're going to add 4 hydroxide ions to both sides of the equation. So notice that adding an equivalent amount of a substance to both ends does not change the reaction. Okay, so it's like if you have 4 plus x being equal to, let's say, 6, right? So if you decide to subtract by 4 on both sides, by adding a -4 both sides and a -4 both sides, you are not changing the equation. Okay, and that's basically what we're doing here. Now you realize that a reaction between a proton and an hydroxide ion basically gives us what? Water. So on our left hand side, something is going to change about it. So I have 2 manganese O4 2 minus plus 4 water molecules plus our manganese O4 2 minus. Okay, that was our reactants on our left hand side now at this point. And then on our product side, you realize that we add 2 water molecules, which I'm going to indicate, and then derivative have started with water molecules, and then we've now also introduced our 4 hydroxide ions, so plus 4 hydroxide ions. What else? We now also have, oh, I'll write what was there, manganese O2 and 2 manganese O4 minus. So clearly at that point we'll be able to see that we have got spectators, because we have water on both ends. We've got 4 water molecules, we've got 2, so we'll have to subtract. So those 2 ones, we'll subtract 2 water molecules on both ends because it's a lower one, right? So clearly the 2 ones will go here, they'll reduce from 4, they'll become now 2. Now this is our final equation in alkali or basic media, and this is basically how you go about this method of ion electron method in basic or alkali media. I'll just introduce us to oxidation numbers. So I'll first of all basically introduce the rules of assigning oxidation numbers before we could get to answer these 3 questions that I have with me. Okay, so what is an oxidation number? So before I get to define what an oxidation number is, we need to understand that an oxidation number is also known as an oxidation state. Okay, so what are we saying? An oxidation state, also known as an oxidation number, can be defined to be the number of electrons that can either be gained or lost for a chemical bond to be formed. That is basically what an oxidation number state is. Okay, so we've got certain rules that we get to consider when we are assigning oxidation states or oxidation numbers to make our lives easier. Okay, so number 1, the oxidation number of a free or a neutral element is always a 0. Okay, so when you're given a neutral element any element from the periodic table without any sign. Okay, so let's say carbon, or I say oxygen, or I say magnesium. Notice that these are not ions. They are just, I've written them in their elementary form. There is no charge that has been assigned. When they exist in that form, the oxidation number or the oxidation state is 0. Number 2, the oxidation number of a monoatomic ion is equal to the charge of the ion. Okay, so now we are talking about the ions. So I'll use these very examples. Let's say O2 minus, magnesium 2 plus. Okay, so now you see that these are now monoatomic ions, right? So their oxidation number is equal to their charge. So in this case, we can say that the oxidation state of oxygen is 2, index is negative 2. The oxidation state of magnesium is positive 2. So except as an oxidation state, we start with a sign rather than starting with a number. Okay, so that is our second rule. Number 3, the oxidation number of group 1 elements is always plus 1. So get any group 1 element, provided it is in a compound. Okay, it is basically having a charge or an oxidation number of a positive 1, group 1. Group 2, they have got a charge of plus 2 in any compound. So don't mix up number 1 with number 2 or number 3. Number 1 is dealing with elements without existing as an element without any charge. Number 2 is talking about ions with their charges. Number 3 is talking about them existing in a compound. Group 1 will have positive 1, group 2 metals will have positive 2. Now oxidation number of oxygen in a compound is typically a minus 2. Oxygen in a compound. Okay. Number 5. Oxidation number of hydrogen is typically positive 1 in a compound. Very simple. Number 6. Oxidation number of fluorine, which is an halogen, is typically always negative 1. Okay. Number 7. The oxidation number of the other halogens, chlorine, bromine, iodine, is typically negative 1 as well, but can vary, unlike fluorine, which is always a negative 1. Number 8. The total oxidation number of a neutral compound is 0. So a very good example is what we have there. So that is a neutral compound. There's no charge here. So since there is no charge, the sum of all the oxidation numbers is going to be equal to 0. And finally, the total oxidation number of elements in a polyatomic ion will sum the charge on the polyatomic ion. Okay, so there are some cases, as we look at some other examples, you'll be able to see we've got the charge here. So the summation of the oxidation numbers of all these elements is supposed to be equal to that charge. And with these rules that we've talked about, we are able to answer all these questions. Okay, so I'll guide on a few, and the others you're able to try them out. So calculate the oxidation number for carbon in each of the following compounds. So the first one has been given to be diamond, right? While we just have a carbon. So what should we expect? So carbon has been given in elementary form. So what do we expect? So according to oxidation number rules, we expect that the oxidation number is a 0. Number 2, carbon dioxide. So I want to find the oxidation number of carbon in the carbon dioxide. So we already know to say carbon, we'll put X to denote it, and then we've got 2 oxygen atoms. Now what is the charge? There's no charge here, is a 0, so the summation of all the oxidation numbers is equal to a 0. Now substitute. We don't know the charge of carbon, I'll put X. For oxygen, we say it is typically negative 2 or minus 2. So we can perform our math here. X is obviously going to be negative 4, going towards the other side will be positive 4. Now what is the oxidation state in that case? So it's positive 4. We can go to calcium carbonate straight away. So for calcium carbonate, calcium is coming from group 2. It's a group 2 metal. So it has got oxidation state of a 2. plus carbon, we'll put X, we don't know. We've got 3 oxygen atoms. Oxygen is -2. There's no charge on the compound, so it's equal to 0. So we'll have X minus 6 plus 2 is equal to 0. So we have X minus 4 equal to 0. So equally here, the charge of our carbon, of the oxidation state, sorry, is equal to a positive 4. Okay. We can go now to baking soda, sodium hydrogen carbonate. What comments can we make there? Sodium is in group 1, so it goes to oxidation state of the positive 1. Hydrogen, we said positive 1. Carbon, we don't put X. Oxygen, we have got 3 times the -2. The charge, 0. So 1 plus 1, 2. Minus the 6 plus X is equal to 0. So our positive X is equal to a positive 4. So the charge of our carbon atom is positive 4, not necessarily the charge, our oxidation state. Okay, so I've answered question 1. Very, very simple and straightforward, as you can see. We're on question 2. We are assigning the oxidation number for chlorine in each of the following given ions. Okay, so we've been given first of all the first one with a charge of a minus there. So the important root to understand here is we said the oxidation states, the summation of the oxidation states of the elements of the atoms present is equal to the charge of the compound. So in this case, we don't know the oxidation state of chlorine, so put X plus the oxidation state of oxygen is known to be a -2, equal to the net charge of the compound, which is a -1. So X is equal to -1. The -2 goes the other side, it will be a +2. So ultimately the charge becomes a +1. Not necessarily the charge, the oxidation number, sorry, of the oxidation state. And then on the other part, equally will do the same. So here we have that. So the charge is supposed to be on top. We'll put X for the chlorine. Oxygen, we've got 4 oxygen atoms. Each has got a charge of a -2. Sorry, the oxidation number. The net oxidation, the net charge of a compound is a -1. So we have X being equal to -1 plus 8. So our charge, oxidation number, in this case, becomes a 7. This is how simple it is to deal with these. We can go to the last question. Feel free to pause the video and try out this one. Okay, so from oxidation rules, we already know to say sulfur has been written in form of an ion. So obviously the oxidation number is directly equal to what? -2. We can go to the other one. So there we'll say S would denote sulfur itself. We've got 3 oxygen atoms, each with an oxidation state of a -2. The net charge of a compound is a -2. Sulfur is equal to -2. 3 times -2 is a -6, because outside it becomes a +6. So sulfur here has got an oxidation number of a +4. Okay, simple, right? This is how simple it is to deal with calculations of oxidation numbers. Okay, very, very simple to deal with them. So just observe what we've been given, perform necessary calculations, and you'll be able to get your answer. We're just going to talk about the balancing of redox reactions using the oxidation number method. Okay, so if you've not watched the video now to assign oxidation number, do watch it. The link is in the description. So the first thing that you'd want to do is first of all identify what is necessary for you to balance in terms of oxidation states. So in this case, I'm able to see that iron is related to the iron on the other side, and then I'm able to see that carbon is also related to the carbon on the other side. Notice that oxygen is usually standard, and of course we know its oxidation state. So we have to observe the change in oxidation state of iron, okay, and then also the change in oxidation state of carbon where it is existing. Okay, so let's start. So we'll look at this. We'll drop it there. So we don't know the oxidation state of iron in that compound. What are we going to do? We'll write the oxidation state. We'll say X. Let X denote what? Ion. How many do we have? We have 2. So we're going to have 2X plus 3. We've got 3 oxygen atoms. The oxidation state of oxygen is a -2, equal to the net charge of a compound, which is a 0. So we have 2X. 3 by -2 is going to be -6. Goes the other side, becomes a +6. X is equal to +3. Okay, so in cases where you don't have enough time, just observe to say there's that 3 there, which is on the oxygen, is coming from the ion. Okay, so the oxidation state of ion in this case was 3. Okay, so we have a +3 for ion. On the other side, since it is existing in the elementary form, there's no charge there, so it's 0. Those are the rules of oxidation states. Carbon, quickly. So we don't know there, so we'll say let X denote carbon. The oxidation state of oxygen is a -2. The net charge of carbon monoxide is a 0, so X becomes +2. So what is the oxidation state of our carbon there? +2. And then finally, carbon dioxide, let X denote carbon, and then we've got 2 oxygen atoms with each a -2. The net charge of carbon dioxide is 0, so X becomes +4. So what is the oxidation state of carbon in that one? So +4. What do we do? So let's try to observe the changes in oxidation state. I'll start by observing first of all for iron. We're moving from +3 to 0. What's the change? The change is +3. 3 to 0, the change here is a 3. The other observation we can make is from 2 to 4. What's the change? 2 to 4, the difference is what? A 2. So that's our change. So what do we do now? So what we do is we basically get to multiply everything by the opposite charges so that we balance. Okay, so this 3 is going to apply to everything on the other side, on the other half part. So it is going to apply to the carbon monoxide and also the carbon dioxide. And then I also use the 2. The 2 now also apply to the other opposite side. It would apply to the ion, the first part and also the other part. Now if you get to observe, notice that we already have 2 there, 2 ion atoms. The other side we have 2, so we can't put the 2 here. So this is an indication that it's not every time that we get to consider the multiplying of the 2 there, or the opposite charges or the changes in the oxidation states. Okay, but if you observe for carbon monoxide, realize that it was necessary for us to apply the 3 to both the carbon monoxide and the carbon dioxide, because the number of carbon atoms are now balanced. Okay, so it will not, the 2 will not apply to this first part because we already have 2 ion atoms. Okay, so what do we have now as balance equation? So what remains there is now your balance equation. Okay, that is how it basically gets to go about it. Okay, so we're on the other question now to understand better on what we need to do and what we need to consider. So look at this. Here we have copper, hydrogen is standard, oxygen standard. So observe, we are more interested in copper and nitrogen, since the oxidation states of hydrogen and oxygen are known. Okay, so let's make an observation in copper first of all. As we check the other side, what do we observe? So copper here, first of all, in the first part, it is existing in its elementary form, so it has got an oxidation number of a 0. On the other side, by just observing that there is 2 there, just like I told you for iron, the fact that we add something like this, so when you're forming the formula of a compound, you look at the oxidation states. So there's an exchange of oxidation states. So there was a swapping like this. That's why I'm saying the 3 there was denoting what? The oxidation state of your ion. So the same applies to what we have. The fact that we have a 2 there indicates that we had copper 2+, exchanging with a nitrite, which has a charge of a -1. Okay, so therefore we can say we have copper 2. And then we can observe for nitrogen. I'll drop part, I would have to make some calculations there. So we know hydrogen has got a charge of +1, oxidation number of 1. We'll put X to denote our nitrogen. We've got 3 oxygen atoms, each with a -2, equal to 0 because the charge was 0 there. So we have X being equal to 3 multiplied by -2 give us a -6. -6 plus a 1 will give us a -5. Goes the other side, becomes +5. So there the initial oxidation state is +5 over nitrogen. We go the other side. We have nitrogen dioxide. So X denotes nitrogen. We've got 2 oxygen atoms. The net charge of a compound is 0. So X becomes +4, right? So we've made an observation there. Okay, now that we've made the observation on the changes in terms of oxidation number, for copper we've noticed that there was a change of from 0 to 2, which was a 2. Okay, and then for nitrogen we've observed there was a change of a 1. So for nitrogen it's going to apply to the copper. We'll add the 1 and the 1. And then for the nitrogen there was a change. For copper there was a change of a 2, which will now apply to the nitrogens, right? Okay, now you also need to make some observations, because it's not necessary that whatever you add is going to balance things up. Okay, so let me just try to erase. So we'll start with copper. On the left hand side you have a single copper, on the right as well 1, so balanced. Hydrogen atoms, we have 2 there, we have 2 there, balanced. Nitrogen, 2 there, 2 there, so here there are 2, there we also have 2, balanced. Oxygen, here you've got 3 times 2 giving us 6. The other side, 3 times 2 you have 6, plus 2 times 2 we have 4 more. The other side you have a 1, so you have 6 plus 4 giving us 10 plus 1, 11. So I have 11 on the left hand side, actually of 11. So that's basically not balanced. What can we do to try to balance it up? So observing that we have 11 the other side, and then this other side we have 6, I think it would be much better if we try to double there. So if we make it from 2, we can make it 4. So if you make it 4, you realize that we have 12 now on the other side. So we are closer. So here you now have 12. There you have 11. So we can only make it equal if we can multiply the order that is on the right hand side by a 2. So that you've got 2 oxygen atoms plus 10, making it 12. Now that also balances out the number of hydrogen atoms, since we now have 4. There you also now have, how many do you have here? 2 times 2 gives us 4. Now the nitrogen atoms, how many do we have? Here you realize that you have got 2 there. So I think this is a mistake that we made when counting for nitrogen. So nitrogen necessarily didn't basically balance up at the time I was asking. So nitrogen on the left initially we had 2. There we had 4. Yeah, there we had 4. So it was necessary that we had to multiply. But I can just redo that again. Okay, so if we try to observe nitrogen, here we have got 2. The other side we have, we have 2 there plus also 2 there, giving us 4. So we have 4 nitrogen atoms on the left. So we can only balance if we can make it 4 as well this side. So I'll remove the 2 so that it now becomes 4 as well. So we have nitrogen atoms. Now the moment we add that 4, there will be a change to our hydrogen atoms. We now have 4 here. How about the other side? We only have 2. So I'm supposed to add the 2 here to make it 4. Now we've balanced the hydrogen and nitrogen. Let's observe oxygen. Oxygen here we have got 4 times 3 giving us a 12. the other side 3 times 2 is 6, 2 times 2 is 4, and then there we have 2 times 1, that is 2. So 6 plus 4 plus 2, that is also 12. So we've now balanced the entire equation. The number of all the atoms on the left and the right hand side are actually balanced. So oxidation numbers give us a starting point, and it makes things easier. If you try to balance the directory, it's going to be more complicated. So basically, this is an introduction on how you get to balance redox reactions using the oxidation number method. In this lesson, we're just going to understand the concept that lies behind back titration. Okay, so back titration involves two reactions where you have a reactant used in the first reaction, and then when it's left over, it is used in the second reaction. So the main essence of the second reaction is to determine how much was in excess, and then subtract from the initial to get how much had reacted in the first reaction, and use that information to determine the number of moles of a substance of a known concentration or unknown number of moles. Okay, so look at this question to help us understand what is basically happening. Alright, so Bishonga was asked to determine the mass. Okay, so in this case they were asking us to find the mass of our calcium carbonate present in the 0.125 grams sample of chalk. Bishonga placed the chalk sample in 250 milliliters of conical flask and added 50 milliliters of 0.2 moles of HCl using a pipette. So if you observe that in our first reaction we have actually calcium carbonate reacting with what? With a hydrochloric acid. Okay, so what is our first reaction? Again, quickly write out the equation. So we have HCl reacting with the calcium carbonate, which is contained in the chalk, and then the excess hydrochloric acid was titrated with, so that is our second reaction. So the excess HCl was titrated against sodium hydroxide. Okay, so what are the products there? So we have HCl reacting with sodium hydroxide to give us sodium chloride plus water. Okay, so what about the reaction between HCl and calcium carbonate? What products are we expecting there? So what we're going to have is calcium chloride plus water plus carbon dioxide. Okay, so that is our reaction there. So this is what back titration is all about. So we have the same reactant in the first reaction and then reacted again in the second reaction. So there's an aspect of it being in excess or being more than enough. Now we are using that piece of information. We are trying to determine what was in excess, and then remember that we are able to find the initial number of moles. So subtract the initial number of moles minus the excess to get how much had reacted in the first reaction. So the number of moles that had reacted in the first reaction will help us to determine the number of moles of calcium carbonate by using stoichiometry. Now if we're able to find the number of moles of our calcium carbonate, remember that we do know the molar mass of calcium carbonate. So at that point we're able to find what? We're able to find its mass. So quickly, we'll start first of all from the second reaction. Now in our second reaction, what we had was we had 0.25 moles of sodium hydroxide reacting. Its volume was 32.12. So we can quickly find its number of moles. Now we have 0.250 moles per liter, and then we are multiplying by 32.12. So milliliters, would have to take that to liters by dividing by 1000 or multiplying by 10 to the power negative 3. So we now have our volume in liters. So at the liters can cancel out. So grab your calculator there and perform your calculation. 0.250 multiplied by 32.12 and then divided by or multiplied by 10 to the power negative 3. So I'm getting 8 of course, that is 8.03 times 10 to the power negative 3. So these are the number of moles of our sodium hydroxide that had reacted in the second reaction. Okay, so I can put sodium hydroxide. So why was it necessary for us to write the equation? So I've written the equation so that we're able to see the number of moles. So hydrochloric acid and sodium hydroxide are in the ratio of 1 to 1. So per every mole of sodium hydroxide, there is a mole of hydrochloric acid reacting. So now that we have determined the number of moles of sodium hydroxide, we now have the number of moles of what? Of hydrochloric acid. Since these guys are in the ratio of 1 to 1, you can show that this way. So if you look at HCl, and then you're comparing it against sodium hydroxide, these ones are in the ratio of 1 to 1. So we can say 8.03 by 10 to the power negative 3 is the equivalent number of moles of what? Of our hydrochloric acid that were in excess. Remember, this is the second reaction. We had already reacted our hydrochloric acid from the first reaction. So this is how much had remained by using the mole ratios. Okay, so we are done with our second reaction. Our second reaction is no longer important. Okay, we call it back titration because we start from the second reaction. So we'll call this to be the excess number of moles of hydrochloric acid. Now, if you go to the question, you realize that we were given the information for our initial amount present of hydrochloric acid. So Bishonga placed the chalk, which contained the calcium carbonate, in the 250 milliliter conical flask, and then he added 50 milliliters, 0.2 moles of hydrochloric acid. So there we are able to see concentration and volume as well. So we should be able to find the initial number of moles of hydrochloric acid that were present in the first reaction. So the concentration was given to be 0.2 moles per liter. Now we're multiplying against the volume, which was 50.0 milliliters. So we multiply by 10 to the power negative 3 or divide by 1000 so that we can have our volume in liters. So 0.2 multiplied by 50.0 times 10 to the power negative 3. So our answer, or our initial number of moles that were present of hydrochloric acid, 0.01 moles were initially present. So now understand what is happening here. What is happening is you have been given the initial number of moles that were present. Okay, now you add the main basic idea is in back titration you need to use a reactant of known concentration and volume, and that is basically what we did. And that reactant is supposed to be in excess so that it is capable of reacting in another reaction. Okay, now in another reaction we're supposed to use another substance. In this case we are using another base of known concentration, and we use titration to determine the volume. Okay, so that will help us to determine the number of moles of the other reactant, and then use it to determine the number of moles of the reactant coming from the first reaction, in this case which was hydrochloric acid. Okay, so these are the number of moles that were initially present. Now these are the number of moles that were in excess, determined from the second reaction. So we're able to subtract the two guys to find the number of moles now that had reacted, because if this is what was initially present and then this is what was left over or in excess, the difference is what had reacted or what was used up in the first reaction. So you can subtract the two, hoping that you've understood the concept behind back titration. So the difference is I'm getting a value of 1.97. So the number of moles that had reacted of hydrochloric acid in the first reaction, I'm getting 1.97 times 10 to the power negative 3 moles. Okay, so we'll observe now the mole ratios again. What mole ratios are we able to observe? Is the reaction balanced already? So these guys are in the ratio of 1 to 1. So if the guys are in the ratio of 1 to 1, what does that tell us about our calculations? So if in the ratio of 1 to 1, tells us to say the number of moles of hydrochloric acid that had reacted is basically equivalent to the number of moles of HCl, of our calcium carbonate that was present. But if you notice, if you look at the equation, you realize that it is not balanced. So we'll have to balance it properly. What is the difference, sir? So we have got two chloride ions on the on the right hand side. So we have to put the 2 on the HCl there to balance it up. So we have calcium chloride there. So we've now balanced the equation. So these guys are in the ratio of 2 to 1. In that case, we realize that if we're comparing HCl to our calcium carbonate, per every 2 moles of hydrochloric acid, there should be a single mole of calcium carbonate. So if you have 1.97 present, you'd have to expect it to become half of it. Or you can put x there and cross and multiply. You still end up dividing by a 2. So per every 2 mole of hydrochloric acid, there's a single mole. So there is it's being halved. So we have to half the to multiply by half or divide by 2. So we basically do that. Now what I'm getting is 9.85 times 10 to the power negative 4. Now these are the number of moles of what? Of our calcium carbonate that had reacted in the first reaction. Okay, so we used back titration to find the number of moles of calcium carbonate. Now a question that you can ask yourself is, at this point, how do you basically get to find the mass? How do you get to find the mass? So notice that we have been given the formula of calcium carbonate. So we're able to do what? We're able to find its molar mass. So calcium, the molar mass is 40. Carbon, that is 12.01. Oxygen, that is 16. Approximately value that you're going to end up with as the molar mass of our calcium carbonate. I believe you're able to use a periodic table. So the molar mass is 100.0869 grams per mole. So you have your molar mass and then you have your number of moles. How do you find the mass? Realize that the number of moles is basically mass divided by molar mass. And looking at the units, if I look at my units for my molar mass, it's grams per mole. So I can say per every mole there is 100 and 0.0869. Per every mole of what? Calcium carbonate, there is 100.0869 grams. Okay, and then what are we doing? We want to find, our main goal is to find what? Our main goal is to find the mass. So there wasn't a need for us to exchange that. We'll maintain it as it is. So we have 100.0869 grams per every mole of calcium carbonate. Now at this point we'd have to multiply that by the number of moles of calcium carbonate. So the mass is the same as molar mass multiplied by the number of moles. So the number of moles will cancel with that, so that you end up multiplying and then you just get your answer in what? In grams. So look at our number of moles multiplied by our molar mass. What answer are we getting? So after performing all the calculations, the result that I'm getting is 0.098598 grams of calcium carbonate was present in the chalk. So basically this is how you handle such a question. There may be some cases where they can ask you to determine the mass percentage of our calcium carbonate in the chalk. So you'd have to divide what you've calculated there divided by the actual mass. Okay, so basically, or in other terms they call it percentage purity, determine the percentage purity. So basically this is how much was pure, the rest of that mass was impure. So you'd have to divide the two and multiply by 100 to get the percentage purity. So hopefully you now understand the concept that is behind back titration and how we basically get to work with it. Two reactions will be given. the first one of the reactants will be in excess and will react in both reactions. Start from the second reaction, determine what was in excess, determine the initial number of moles, subtract to get how much had reacted, use the stoichiometry to find the number of moles of a substance of unknown number of moles or unknown concentration.